Hello and welcome to the first episode of VoltLog. This will be a product review and teardown of the Gophert CPS 3205. This is a 32 volt 5 amp adjustable switch mode lab power supply with active power factor correction. Gophert makes quite a wide range of power supplies, but I went for this particular model because it covers my lab requirements. The maximum voltage of 32 volts allows me to power a great majority of projects that I'm working on, even 24 volt systems if work on such systems is required, and the maximum output current of 5 amps will definitely cover pretty much everything I'm working on. And as a general rule, you would want your lab power supply to be able to output at least 24 volts and 2 amps to cover, as I said earlier, a great majority of circuits and projects that you might be working on. As for noise and accuracy, Gophert claims this power supply will have less than 30 millivolts output noise peak to peak and a set accuracy better than 0.3%. The unit is quite compact, measuring approximately 180 by 120 by 55 millimeters and weighing only 900 grams. The main reason this unit is so compact is the fact it is a switch mode power supply as opposed to a linear power supply, which would have to be much bigger for the same power output. But this type of power supply does have its drawbacks when we talk about output noise later in this video. I got my unit from AliExpress from Gophert Technology for $95 with free shipping by TNT. The power supply does have a good feel. It is an aluminum case, certainly makes it look professional, and the build quality of the case is good. The power supply has voltage and current display on the front, each through a 4-digit 4-segment green LED display, complete with constant current and constant voltage LED indicators. Voltage and current can be adjusted through this rotary encoder, which has detents and has a reasonably good feel when turning. By moving this small black switch, you either set the voltage or the current, and by pressing the rotary encoder you select which digit you want to adjust, and that digit gets highlighted on the display. The voltage and current settings are remembered when the unit is powered off, so you don't have to readjust every time you power on. And the main drawback of this display is that it's not as bright as I would like it to be. I'm not sure if it's the LED modules themselves or if it's the drive circuitry, but this could certainly be improved to get better visibility out of this display. The rotary encoder does not have velocity sensing, but since you can select the digit you want to adjust, I don't see that as a problem. It gets the job done. Lock button on the front panel locks the user interface, so you can, for example, adjust your power supply for a certain voltage and current. You then press lock and you can't accidentally touch the controls and change the settings. On-off button simply controls the output of the power supply. Press this button and the current display will show off. Oh, it was locked. You have to first unlock it, and if you press the on-off button, the current display will show off, meaning the output of the power supply is off. If you press this button for 5 seconds, it will display D on or D off, and that's how you control the behavior of the power supply at power on. If D on was displayed, it means you've automatically enabled the output of the power supply at power on, or if you set it to D off, it means the power supply will come on with its output off. This is an important protection feature that every power supply should have. You don't want to have, for example, your power supply set for 12 volts and have it automatically turn on when you have a 5 volt circuit connected to it, for example. On the back of the power supply we have the IAC mains input. No external accessible fuse, but I bet there is one inside, and we'll check that later when we take it apart. The output sockets, which are standard 4mm, they are not standard spacing, however, at 19mm. They are actually spaced at about 27mm. And we also have the on-off switch. Of course, having all this on the back is not ideal, but considering how compact this is, I understand it can be difficult to design them into the front panel. So it's something you have to decide for yourself. Is this something you can work with? The actual case has no vent holes, and it seems the power devices inside are attached to the sides of the case, because I see these screws on the side of the case, and they will dissipate heat through this outer aluminum body. For the next part, I'm going to measure some of the specs of this power supply and see what I get compared to its spec sheet. I'm going to start by looking at the accuracy of the voltage and current meter on this power supply, which according to its specs should be better than 0.3% plus 1 digit for the voltmeter and plus 3 digits for the current meter. For comparison, I'm going to use my Fluke 87, which was last calibrated about 2 years ago, so I trust its measurements. So let's start with the voltmeter. I'm going to turn the power supply on. The power supply is set to 2 volts and the Fluke 87 agrees. Now let's adjust the voltage to different levels. 5 volts, perfect. 10 volts, the Fluke 87 agrees. 15 volts, yeah, no problem. That's 20 volts, the Fluke 87 once again, it's almost spot on. If I give it some time to stabilize the measurement, or maybe stabilize the power supply regulation, it matches perfectly. Let's go to 24 volts, yeah, once again, no problem. And the maximum output of this power supply is 32.3 volts. This power supply is spec'd as a maximum output of 32 volts, but of course you need to go a little bit higher than that to ensure you do output the spec 32 volts. To test the accuracy of the amp meter, I'm going to use a Fluke 87 in series with an adjustable dummy load. Just as a reminder, the amp meter accuracy should be better than 0.3% plus 3 counts, which, for example, for 100 milliamps output, the amp meter should not be off by more than 3 milliamps plus another 3 counts. I'm going to start testing at 50 milliamps, and I'm going to consider the Fluke 87 as the base measurement. And in this case, for 50 milliamps passing through, the power supply is showing 56, so it can be said it is way out of spec. Next, I'm going to adjust for 100 milliamps. I'm looking at the Fluke 87, and for 100 milliamps it seems the power supply is showing exactly the same difference as for the previous measurement, that is 6 milliamps extra. Let's check the accuracy for 200 milliamps. It seems it's almost the same difference between the measurements, 5 or 6 milliamps. Let's go at 300 milliamps. Close to 300 milliamps. The amp meter on the power supply is showing exactly the same difference as before when compared to the Fluke measurement. That is 5 or 6 milliamps extra. Let's check at 400 milliamps. It seems that as we go up, the error seems to go down. And to show you exactly that, I'll take several different measurements and make a graph out of them to show you how the error evolves when moving upscale on the amps range. But before we do that, let's check a final measurement for 500 milliamps. We seem to have only 3 or 4 milliamps extra on the power supply ammeter, which on this output current is within the specification. of this power supply. I have measured and registered different values from the Fluke and the Gophert ammeter, and by looking at this graph, on the x-axis we have the different measurement points I took in milliamps, and on the y-axis we have the difference between the Fluke ammeter and the Gophert power supply ammeter, also in milliamps, so we can consider that the actual error in milliamps. As we can see, as we go up in output current, the error does go down, and the magical point is at 500 milliamps, where we go below the 0.3% plus 3 counts as stated in the spec sheet of the power supply. That is a bit disappointing, meaning you cannot trust the ammeter on the power supply when you're below 500 milliamps to actually show you the right current going out of your power supply or being supplied to your circuit. I might also say that the display update speed is quite good. I mean, we can test that by removing this load, plugging it back in. From what I can see, there are about 3 or 4 updates per second for the display, which is reasonable and good enough for a power supply. I mean, you can't expect to use this power supply like a real multimeter, and 3 or 4 updates per second is good enough for a power supply in my opinion. For this next test, I'm going to use my scope and test if this power supply overshoots when it is turned on. First, I'm going to test for the soft on-off button. I don't expect it to overshoot in this mode because the power supply is already internally regulating. It's just that it has its output disabled, and turning the output on will just connect the output sockets to the already regulating power supply, so I don't expect it to overshoot in this mode. I have my scope connected to the output of the power supply with a ×1 probe DC input coupling. It is set to trigger on a positive rising edge. Let's try a single capture, and let's turn the power supply on. We're at 1 volt per division, and as you can see we have a nice turn on curve and no overshoot for this mode. Let's also try with a hard power on when we switch the main switch on the back of the unit. But for that I'm going to have to configure the power supply to automatically turn on. We've done that. Let's switch the power supply off. I'm gonna set the scope to trigger same as before, and we're going to turn the power supply on, and the output will by default come on. And once again the power supply is not overshooting. This step you see here, it's not actually a problem with the power supply, due to the fact that this power supply has some capacitance on its output and I didn't allow enough time for it to discharge. The output didn't quite start from 0, and that's why we see this step here, but it's not a problem. If I would allow the power supply enough time to discharge its output capacitors, we would not see this anymore. Next, I'm going to test if the power supply is overshooting when there is a sudden change in load, and for that, once again, I'm going to use my 4.7 ohm power resistor, which I'm going to connect using this alligator hook directly to the output of the power supply while it is running and regulating, and this way we will observe on the scope if the power supply will overshoot. I have my scope set to trigger on the falling edge of the signal this time, because the voltage will fall when I'm connecting this load, and we'll see if there is any glitch or if it's going to try to overshoot. So single capture, let's connect the load. As you can see, the upper marker is set at 5 volt, and we're not seeing any overshoot, so it's all good. Next test will check if this power supply is going to overshoot when there is a load connected to its output and we turn the output on. For example, in this case I'm using the 4.7 ohm power resistor. It is connected directly to the output of the power supply, and the power supply has its output switch off, but the voltage is set to 10 volts and the current limit is set to 1 amp. Considering this 4.7 ohm resistor, it would normally go up to about 2.1 amps if there was no current limit on the power supply. I'm expecting this power supply to overshoot because I took a look at that earlier and I see it does overshoot a bit, but let's test that. So you see the power supply is set to 10 volts. The scope is set to trigger on the rising edge. Let's turn the power supply on. Okay, so we've captured this waveform and we see the upper marker is at about 10 volts. Yeah, and this is not a precision power supply, so once the output is on, the power supply will go up to its set voltage, which is 10 volts, and it will then try to regulate the current and will go into constant current mode. That takes about 50 milliseconds, under which the current will rise quite a bit due to the rise in voltage. So if you are using this power supply to power some sensitive devices like LEDs, you need to consider that and don't expect it to regulate immediately after power on. You are better off starting with a lower voltage and slowly increasing it until going into constant current mode. Next, I'm going to take a look at the output noise of this power supply, which according to its spec should be less than 30 millivolts peak to peak. I'm going to start by configuring the scope for measuring this. You want to use AC coupling ×1 probe and bandwidth limit on, because these noise figures are usually given for bandwidth limited measurements. As for acquiring the signal, you generally want to be in peak detect mode, because we want to measure all the noise peaks. So peak detect is the best mode for measuring the output noise of a power supply, and you should go to the lowest vertical range of your scope, which is in my case 2 millivolts. For this measurement, you don't want to be using your alligator hook lead, your ground lead from the scope probe, and I'll show you in a moment why. This will act like an antenna and pick up and couple all sorts of noise into your measurement, and you'll get a figure which is way off as compared to a correct measurement method. So I'm going to connect this to the output of the power supply, just like that, and I'm going to try to zoom in on the scope. You see we're getting 80 to 100 millivolts peak to peak noise, and you might say this power supply is way out of spec because in its spec sheet it should have less than 30 millivolts output noise peak to peak, and we're actually getting close to 100 millivolts. But no, that's not the case. We are actually picking up all sorts of noise from the room because we're using that ground lead from the scope, which is acting as an antenna. Ideally, for this type of measurements, you would want to use a differential probe to eliminate any kind of exterior influence on your measurement, but those are quite expensive and inaccessible to home or hobby labs. But you can do something. First, you get rid of this ground lead, and in my case I have improvised and placed this lead on the negative terminal, which will allow me to connect the scope probe directly to the output terminals like this. The positive tip of the probe will touch the positive terminal, and this lead will touch the insulation of the tip of the probe, which is actually ground connected. So it should go something like this. Now that I have a nice low impedance path for the between the scope and the power supply, you might think this is the real measurement figure, but it's not the case. With this scope, with this O1 scope, we're now getting between 40 and 50 millivolts peak to peak noise figure. But watch what happens when I disconnect the AC power lead of the scope and leave it running on the battery. Quite a bit of noise reduction in our system. I don't know why that is happening. The scope is obviously influenced by noise induced from the AC power line, but it's clear that without that AC power lead and the scope running just on its batteries, we're getting a noise figure of 7, maximum 8 millivolts peak to peak, which is well within the spec of this power supply, which states it should be less than 30 millivolts peak to peak, and I can certainly work with 7 millivolts peak to peak noise figure. It's not exactly a low noise power supply, but you have to keep in mind that this is a switch mode power supply and not a linear one. So we got our first noise figure of approximately 7 millivolts, but that was with no load connected to the power supply, and that figure might change slightly if we increase the load on the output of the power supply. So for that I'm going to use a power resistor connected on the output terminals of the power supply. I'm going to slowly adjust the current limit and see if the noise figure increases. So for 500 milliamps we're still getting 7 to 8 millivolts peak to peak. Let's see for 1 amp. At 1 amp we're still getting 7 millivolts of peak to peak output noise. That's quite good. I mean, from 0 to 1 amp output load we see basically no increase in the output noise. Let's go even further. Let's go up to 2 amps. So you see with this load I need to increase the output voltage to increase the current. So now we're at 2 amps. We're outputting 2 amps from this power supply, and the noise figure increased to somewhere between 9 and 10 millivolts peak to peak, which is also acceptable. But let's go even further. I'm going to increase the output voltage up to 24 volts. Let's make it 25. Now I'm going to adjust the current limit on the power supply. Let's go up to 3 amps. So at 3 amps we're getting 15 millivolts of output noise peak to peak measurement. Let's go to the maximum of this power supply. At 4 amps we're getting 25 millivolts, and at its maximum output rating of 5 amps we're getting 42 millivolts of peak to peak noise, which is exceeding our spec, but that is during constant current mode, and I'm not expecting any power supply in this price range to meet its output noise spec at its maximum output range. Before moving any further with this power supply review, I would like to mention something I noticed about the output of this power supply. It does have a large amount of capacitance connected on its output. The designers probably chose to do that in order to reduce the output noise, but you do get a negative effect out of that, which means you store a lot of energy in those output capacitors, and you cannot really control that, how that energy is discharged. So for example, before the current limit kicks in, you are discharging all that energy into your circuit and possibly damaging your circuit. That also happens when you turn the output of the power supply off. I'm going to show you that right now. You see the output voltage slowly goes down and discharges. So the on-off switch on the power supply actually turns off the output before the output capacitors. That's not really a good design choice, because as I've said before, it can be dangerous and it can damage your circuits, so you need to take that into account and remember it. Next, I'm going to take a look at the internal electronics of this power supply. To do that, I'm going to need a Phillips screwdriver. There are 4 screws on the back. This will probably remove the back panel. Now, starting from the AC input of this power supply, I already see something I don't like. There is no heat shrink on the AC input terminals of the IAC main socket. It is generally desirable to heat shrink these input terminals to improve the safety of the power supply, but in this case we have no isolation on the input terminals. Moving forward, the earth lid is soldered on the PCB. It looks like nice solid connection, and the PCB itself has a connecting tab, making the case mains earth referenced. We also have shake-proof washer in there, so there is no risk of this vibrating loose. Continuing, we do see the input protection fuse that I mentioned earlier. We don't have it accessible from the outside. Unfortunately, it's not a socket one, so it's not easily replaceable. You would probably need to get in here, desolder this, or at minimum remove this heat shrunk and replace the fuse. I understand that lowers cost during production for not adding an extra socket for a fuse, but it's not really acceptable in a lab power supply. A lab power supply should have its fuse socketed so you can easily change it. Continuing, after the input protection diode, we see a pair of Y caps and a pair of chokes filtering the mains input, which goes into this bridge rectifier. At the output of this bridge rectifier, I know for a fact from the specs of this power supply that we have a power factor correction circuit, and it's an active one because I see these devices connected to the transformer. They're probably a MOSFET and a diode. In fact, in Europe, all power supply must have some kind of power factor correction circuit, either passive or active. But in this power supply, because of these devices, I know it's going to be an active power factor correction circuit. These are the capacitors at the output of the PFC, and on these caps we should have our high voltage DC, which then goes into the actual switch mode power supply. Moving forward, we have this strange looking 7-pin device, which is quite interesting. I've looked it up, and it's a TNY274. It has control circuitry as well as power MOSFET integrated in the same package, optimizing the power supply cost by requiring less components. It's a fairly low power switcher, but I'm guessing it is switching into one of these transformers for generating possibly the 5 volt or whatever voltage they're using for the control circuitry, something like that. Next, we have this chip, which I immediately recognized is the TL494 PWM power control circuit. It is designed specifically for controlling switch mode power supply. I have encountered it numerous times in various power supply designs, and I've also used it myself when trying to design a switch mode power supply. In this design, I'm guessing this is the one controlling the actual output of the power supply by switching this transformer connected between the high voltage DC and the output of the power supply. I've also spotted the first budge in this design. Right here, this PCB track looks like it has been deliberately cut and then it was repaired using a piece of terminal wire, probably from a resistor or something like that. There's probably not much going on the back of this PCB. We might expect a power factor correction circuit IC, because I don't see it on the top side of this PCB, so it might be soldered on the back of the PCB. But other than that, I don't expect to see much on the bottom side, maybe just some supporting passives. So let's take apart the display assembly, because here we might see something interesting. I'm suspecting this front panel is also home to the microcontroller, which is controlling all of the power supply. And we get some crusty flux residue on this PCB, but not so bad. I mean, I've seen worse. It's nice all the terminals are labeled in here. It looks like we're gonna have to remove this rotary encoder knob and these 3 screws to get access to the actual top side of this PCB where all the magic happens. Actually, this PCB looks like it has been hand soldered, and I will switch to a macro lens to get a better picture of that. And there also seems to be like a residue on the surface of the PCB and the actual chips, because it makes it very difficult to read the actual numbers on the chips. It might be a flux residue. For example, if this board has been sprayed with flux entirely, it might be that. I cleaned the flux residue from the PCB and actually from the top of the chips by using some alcohol wipes, and now I'm able to read the name of the devices, and they are as follows. The microcontroller is an STM8S105K4, which is an 8-bit 16 MHz 16 KB flash, 2 KB RAM and 1 KB E2 PROM. It's this device right here. It's not using any external crystal oscillator. It's probably using the internal oscillator, saving some money this way. Next we have these 2 chips, U1 and U2, which are Jelly Bean HC595 8-bit shift registers. They are obviously used for multiplexing the 7-segment display. As for the analog side of things, we have this guy right here, which is an LM358, also a Jelly Bean type part, dual op-amp, and judging by the test points labeled CC and CV next to it, this guy is handling the constant current and constant voltage mode. I don't see any external DAC or ADC on this board. I also don't see any SPI or I2C type pins going off to the connector, which can only mean they're using the internal 10-bit ADC of the microcontroller for measuring current and voltage, and they are using PWM outputs with probably low-pass filters to generate the control voltages needed on the power side of things. Other than that, just a voltage regulator right here, which is also a Jelly Bean type on LM117, which is probably used to power this whole board with something like 5 volts. The front panel PCB seems to be using 220 ohm resistors on the output of the shift registers, which is probably limiting the current to each LED and in turn gives the brightness that we see. Modifying those resistors to a lower value will probably increase the brightness of the display, but would make it more difficult to see the selected digit, since they use a brightness scheme to show the selected digit in higher brightness. The capacitors used in this power supply are a mix of Capson and Samsung, which are basically the cheapest branded capacitors you can get. I would not rely on these capacitors to be used in some high reliability product, but they are all 105 degrees C rated, and the layout of the PCB is nicely done. They've kept away the capacitors from the active power devices that will generate heat. For example, right here, the output caps are quite away from any heat generating device. And even a crappy brand like Samsung or Capson, if they are 105 degrees C rated and they are kept away from heat, they should last you quite a while. Now looking at the output section of this power supply, we can see the inductors filtering the output as well as the output capacitors. And as I was talking earlier, we have quite a large amount of capacitors on the output of this power supply. For example, this one is a 2200 microfarads capacitor. I believe we have another 1500 or something microfarad capacitor here, and another 680 microfarads parallel to the output terminals. So in total we have something over 4000 microfarads on the output of this power supply, and that, as I mentioned earlier, is somewhat dangerous for the circuits connected on the output of this power supply, as even if the current limit kicks in, you still have quite a lot of energy going out through those output terminals. Also on the output of the power supply we have this beefy current shunt, which is used to measure the output current of the power supply, and these two very thick wires, which are more than capable of carrying the rated 5 amps of this power supply to the output terminals, which have a cap parallel right on the output terminals. These have their own PCB complete with shake-proof washers. The only downside of these output terminals is that they are not standard 19mm spacing, so you can use adapters and jigs that have the standard spacing. One thing I don't like on this power supply design is that they don't use separate sense wires for the output voltage measurement. They are tapping the PCB right here on the output terminals, and that of course does not include the voltage drop that you might get on these wires. I do see some PCB pads which they are probably designed to allow connecting a separate set of leads for sensing the output voltage directly at the output terminals, but on this model they are not installed. Now that might be due to the fact that these output wires are quite thick, and the voltage drop that you might get on these wires is not enough to throw off your voltage measurement enough. So maybe it is a design decision not to mount the additional sense wires on this model, because it can only output 5 amps. The PCB looks like it has a gold finish and reasonable good quality. I mean, I've seen worse in Chinese products, and this is not one of the worst I've seen. I mean, with a bit of cleaning, this PCB would have looked much better, but I'm guessing most of the manufacturers in China, they don't really care about how their PCBs look like. They just want to have a functional product so they can ship, so they don't waste extra time or money on cleaning the PCBs. And from a technical point of view, the cleaning might not even be necessary. I mean, if they're using a no clean flux, that is just fine, leaving it on the PCB. There is no problem. It will not corrode or create any leakage problems in time, because it has been tested and it is allowed to be left on the PCB. It's not clear so far if this PCB has been hand soldered. At least some of the components on the back of this PCB have been hand soldered. Not sure about all. They might just be wave soldered, tricking me into thinking it has been hand soldered. But there are some bodges, and at least those, I'm sure they have been hand soldered. I'm gonna try to zoom in on those. There are some capacitors on that side of the board which are stacked. They look like 0206 capacitors, and there is two of them stacked on top of each single pad. One nice thing I always like to see on power supply PCB designs is a clear separation between the primary and the secondary side, and we can see that delimitation with this white line, and we can see there is a clearance between the primary and the secondary side of this power supply. On the back of this PCB I identified this little guy here, U1. It is an ICE 2PCS01 PFC control IC from Infineon, and as I was expecting, it does active power factor correction using the transformer and this MOSFET and diode as I showed on the front of the PCB. There is also this guy right here, an 8-pin SO package, which I couldn't read the markings on it. They are too faded. That guy could be an op-amp or a comparator of some sort, because it does appear to be linked with the output shunt resistor. You see these two tracks come from the output shunt resistors and end up here in this area. So this chip could be an amplifier for the shunt resistor current measurement, or something related with that. I also discovered the second fuse present on this PCB, F2, which is right here, and I believe this fuse separates the high voltage DC generated by the power factor correction circuit from the rest of the power supply. But same as the first fuse, it doesn't have a socket for easy replacement, and its value it's not marked on the PCB, so you'll have to hope the value is stamped on the side of the fuse when you are replacing it, because otherwise you wouldn't know what value to replace it with. Overall, I'm quite satisfied with the construction of this power supply. They seem to be using quality components. I mean, except for the capacitors, which are basically the cheapest brands you can get. They are using branded active components, semiconductors. They're using what seems to be good quality transformers and inductors. The PCB seems to be FR4, so once again, good quality compared to other power supplies coming from China. The only complaints I have about this PCB is, and this assembly in general, is the fact that they did not isolate heat shrunk the input terminals. Also, I'm not happy with bent terminals on the input active devices. Let's see what else. I'm also not happy with the flux residue present on the back of the PCB, but other than that, I mean, there's nothing you can say about this power supply. In terms of repairability, I give it a 9 out of 10 repairability score. You can probably find and replace every last component present on this board, but you don't get marked test points or other markings on the PCB to help you debug, so you're on your own to figure out what's happening and where to measure things on this board if something is to fail. Here are my final thoughts on this Gophert power supply. I think it's a nice, compact and efficient power supply with a good looking aluminum case. You can almost certainly find a spot on your workbench for this power supply for it being so compact. Also, on the plus side, it is a fanless design, so it is a silent power supply, and some people, in fact most people, like their equipment to be silent. The price is not bad either. I paid $95 for this power supply. I definitely think it's worth it. I mean, I wouldn't mind it being any cheaper, but let's face it, they have a cost for manufacturing this and they need to make a profit also. However, I would keep in mind the negative points I found during this review. If you decide to purchase this power supply, you need to be aware of these things. First of all, they are not using good quality capacitors in this power supply, so there is a slight chance that a capacitor will fail in this power supply at some point. Also, there is a high amount of capacitance on the output of this power supply, and that could accidentally discharge into one of your circuits, so damage might occur if care is not taken. Also, this power supply, as I've shown in the review, First it goes up to the set voltage and then it starts current limiting and going into constant current mode. That could be an issue with current sensitive devices like LEDs, which might see a surge of current before the power supply goes into constant current mode and starts the current loop regulation. I would also keep in mind the fact that this power supply exceeds its maximum output noise figure at the higher end of its range at 32 volt output and close to its 5 amp maximum output. As I've shown previously in the video, the power supply does output more than 30 millivolts peak to peak output noise. If you liked the video, please give it a big thumbs up and subscribe for more. Thank you for watching.